So last class I discussed about the fabrication of the organic photodetector and how it's work. Now today I'll discuss the how many structure are there in if you want to design the organic photodetector, structure of the organic photodetector, and some criteria we have to follow to design the organic photodetector that we will discuss today. So structure of the photodetector. So there are the two types mainly. If we think about the design consideration, there are the two types. Okay, one is the bilayer heterojunction. This depends on the heterojunction. Bilayer heterojunction. Second is the bulk heterojunction. Right? So bilayer heterojunction and the bulk heterojunction. So in case of the bilayer, so what are these junctions and what are the advantages that I will tell now. Okay, bilayer heterojunction. In case of the bilayer heterojunction, as you know, the anode and cathode layers are already there. You can design the organic photodetector, right? So in case of the bilayer, there is a p type and another is the n type semiconductor, right? This is anode and this is cathode, p type and n type semiconductor. So this is called as a bilayer. The heterojunction, the interface between these two semiconductors, this is known as the heterojunction. Why heterojunction? Because the energy level alignment between these p-type and n-type semiconductors are different. Okay. So if you think about the LUMO levels for both the p-type and n-type semiconductors are different. Right? So this one material that is deposited, the n-type semiconductor is deposited over the p-type semiconductor. Okay, if you want to design the bilayer heterojunction, this n-type material that should be deposited over the p-type semiconductor. Oh, right? So what are the disadvantages and advantages? If you design the bilayer heterojunction, right? So normally, in case there is a one interface, right? One interface between p-type and n-type semiconductor. So if the light falls onto the device, the exciton, okay, the exciton that will generate into the p-type layer. So after that, I told that in the last lecture, it has to diffuse at the interface and dissociate. It should be dissociate. So for that, it has to cross this much length for dissociation, right? So if we design the bilayer heterojunction, so the exciton diffusion length that should be more for a semiconductor, organic semiconductor. Good. It has to diffuse at the interface before recombine. Okay, before recombine, it has to diffuse towards the interface, right? So if the exciton diffusion length is less, that means before reaching to the interface, if the exciton again recombine, then we will not get the free carriers, right? So for this is the one of the disadvantage for case of the bilayer heterojunction. But if think about the after dissociation, after separation of the excitons, after suppose all the exciton reach to the interface, right? So after dissociation, the here will get electron, here will get hole. Okay. So if the only one single interface is there, hole can easily transport towards the this anode and electron can easily transport towards the cathode. Okay. If any other extra layers are there in the p-type semiconductor and in the n-type semiconductor, hole cannot easily transport towards the electrodes, hole and electrons, because it will, some barriers are there, it has to overcome those barriers, right? So this is the advantage of the bilayer heterojunction. That means due to that we will get a less recombination loss. But so for case of the, that means for case of the bilayer heterojunction, less dissociation efficiency. But low recombination loss. So this is the advantage and this is the disadvantage for case of the bilayer heterojunction. Now how we can design the bilayer heterojunction? Bilayer heterojunction, this can be designed. So there are the two types of the molecules. One is the small molecules, another the polymer molecules. So for case of the small molecule, so how can you design the bilayer heterojunction? So by using the many kind of the physical vapor deposition technique, thermal deposition technique, you can deposit both the layers for designing the bilayer heterojunction. First you have to deposit one layer, after that you can deposit the another layer. Okay, but if you want to deposit the polymer layer, okay, for this the bilayer heterojunction, so device, so you will get the less efficiency. Because why? Uh, but suppose we have deposit, so for that, for polymer material has to dissolve into the solvent. Suppose first material we have deposited using the spin coating technique you have to use, right? So first material, this material I have deposited using the coating technique by using the solvent, right? So for that, after that, if you want to deposit the second layer, okay, it can degrade the first layer, okay, it can degrade the first layer. So due to that, you will not get the proper bilayer heterojunction by using the polymer material, right? So if you want to design the bilayer heterojunction or multi-layer heterojunction, so small molecule material is the suitable material, right? Next I will come to the bulk heterojunction. For case of the bulk heterojunction, okay, so like this. Okay, so suppose this is P type, the antimatter. So how can you design the bulk heterojunction? The P type and antimatter both are intermixed with each other. Okay, like if you want to design, if you want to make any kind of the solution, right? So all the materials you have to mix, right? So in this way you can design the bulk heterojunction, intermixing of the P type organic semiconductor and the n-type organic semiconductor. So what is the advantage if you design the bulk? So what I told, if the exciton diffusion length is less, so before reaching to the interface, the exciton will be recombined, right? So this thing will not be happen in case of the bulk heterojunction, because suppose the exciton is generated, right? This is the exciton, so it will easily reach to the interface. Okay, it will easily reach to the interface. If exciton diffusion length is 2 nanometer, that also the exciton can be dissociated, right? So that means we will get this dissociation efficiency, that is more. Dissociation efficiency is more. Okay. Due to the multiple interfaces, exciton can easily dissociated at the interfaces. Whatever excitons are produced, all the exciton can dissociate into the at the interface, right? But disadvantage, this is the advantage, right? Disadvantage is that, right? Reason is that suppose this here I am getting hole and here I am getting electron, right? Now this hole has to transfer towards the anode and electron has to transfer towards the cathode. As there are the lots of barrier, you can see lots of barrier, so the hole cannot easily collected by the anode, and also electron cannot easily collected by the cathode due to these interfaces, multiple interfaces. So for that, so less response we will get. So after dissociation, electron this process should be very fast, very quickly electron and holes should be moved towards the electrodes, right? Though we apply the high reverse bias, still also we will not get high response. So for that is the disadvantage of the bulk heterojunction. So due to that we will get the low mobility and poor hooping transport, right? But exciton dissociation efficiency is more in case of bulk heterojunction. So it depends on the situation and application, what kind of the device. Sometimes the bilayer heterojunction is suitable, sometimes the bulk heterojunction is suitable. Now coming to the fabrication point, how can you design the bulk heterojunction? So I told you this is the intermixing. So if we use the small molecule, so if we design the small molecule based bulk heterojunction, that is a little bit complex, because so co-evaporation. At the same time, the both p type and antimaterial should be evaporated into the air, and it has to transfer on the substrate. Okay, so that is a co-evaporation by using the thermal technique. So if we use the polymer material, that is suitable for the bulk heterojunction, because for polymer material, that is the intermixing. So you can easily intermix two different kind of the materials in the solvent, right? So we have to intermix two different kind of the materials, p type and n type materials, into the solvent. After that, it can easily deposit. So for that, only one layer is required for deposition, because first we have to intermix both the layers, and after that we can deposit this layer, the solid mixed layer, okay, over the substrate or ITO coated substrate. So the polymer material is suitable for bulk heterojunction, and the small molecule material, that is suitable for the bilayer heterojunction. This is about the types of the junction. Now coming to the what are the conditions and criteria we have to follow for designing the organic photodetector. So today I'll focus on the few points, and next class I will continue this thing. Okay, just, criteria. Okay. First is the selection of the p-type material. How can you select the p-type material? Okay, so for that, if you want to design this organic photodetector, mainly is that it has to absorb light, right? It has to, suppose if you want to do a visible photodetector or infrared photodetector or a light photodetector, it has to absorb such kind of the light. So normally, so the structure is like that, right? First is the ITO anode, transparent anode, then p-type, and then cathode. So mainly this p-type material is the absorption material. Okay, p-type material is the absorption material. It transfers through the ITO. Normally, so what are the absorption criteria that should be follow for the p-type material? So if n low absorption is there in n, for case of the n-type material, it may sufficient. Okay, but for case, so suppose if you want to absorb the red light, okay, so the red light, the energy of the red light, that should be greater than the band gap of the p-type semiconductor. The energy of the red light, that should be greater than the band gap of the p-type semiconductor. In this way, so by using the E equal to AC by lambda, we can calculate the band gap of the semiconductor. What kind of the semiconductor will be suitable for absorbing such wavelength light, right? And so normally visible detector, normally you can design by using the organic photodetector. The band gap range for p-type semiconductor mainly 0.7 to 1.2 electron volt. Okay, this is a band gap range. Band gap means for case of the organic semiconductor, the difference between HOMO and LUMO of the semiconductor, this is the band gap. Okay, so this range is this one. So if such kind of material if we use, by using this material we can design the red light, visible light, UV light photodetector, as well as the infrared light photodetector. After that, so absorption coefficient should be very much high. This is 10 to the 5 per centimeter. This is the absorption coefficient. So if we choose any material which band gap is similar to the suppose such wavelength, but that at that particular point the absorption coefficient should be very more. Okay, so suppose if we see the absorption curve, this is the high peak at red light, right? That means we can use. Suppose in any kind of the semiconductor, you are getting the low peak at red light. We cannot use this semiconductor for red light detection purpose, right? Next is the mobility. So this is related to optical properties, right? So next is the electrical properties. So after generation of the acetone has to transport, and after dissociation of the acetone, the carrier should be the hopping transport of the carrier should be proficient. Okay, so that for that the mobility, mobility of the electron and hole, for case the p-type semiconductor and the semiconductor, for both the organic semiconductors, the mobility should be high, because it strongly affects the hopping transport of the carriers. So we have to choose such kind of the semiconductor which has high vertical carrier mobility, because if we design the vertical structure, so vertical carrier mobility should be very much high, right? So this about the electrical and optical properties. And some mechanical properties and thermal properties are not too much important for designing the organic photodetector. Next is the so suppose if suppose we have found five types of the p-type semiconductor and five types of the n-type semiconductor. This has a high good optical and electrical properties. This has good electrical properties. But what kind of the p-type material should be suitable for a what kind of the n-type material? Okay, there is a perfect combination should be there. Okay, perfect combination for particular p-type material with the particular n-type material. That means the energy level between the p-type semiconductor and n-type semiconductor should be matched very well, right? So what are the criteria you have to follow for designing the, for case of the organic photodetector, there are the four processes, right? Evolution, diffusion, dissociation and collection. So to follow, for getting the proper transport or proper process, okay, so energy level alignment between the p-type semiconductor and n-type semiconductor should be very matched, right? So these what are the criteria should be followed for choosing the p-type material with respect to the n-type material? This I will discuss on the last class, right? So for choosing p-type and n-type material, we have to choose some criteria. We cannot choose randomly such kind of the p-type materials and the n-type materials for designing the organic photodetector. Right? So these criteria I will discuss on the next class. Thank you.